Hi, in the last two sessions we were discussing about solvable groups. In this session we discuss about nilpotent groups. While defining the solvable group, we introduce the commutator subgroup G1 of G. And it can be shown that G is abelian if and only if G1 is equal to E, because G1 is the commutator subgroup of G. It's a subgroup generated by all commutators formed by the elements of G. So if x and y is in G and G is abelian, then xy, x inverse, y inverse is equal to E, and vice versa. Therefore, G is abelian if and only if G1 is equal to identity. Then what we did was we iterated the process and we defined the commutator subgroup of G1, we denoted it as G2. And commutator subgroup of G2, we denoted it as G3, and so on. So we obtain a series of subgroups of G, namely G is equal to G0 contains G1, contains G2, and so on. And we have proved that G is solvable if and only if this series, the commutator series, reaches E in a finite number of steps. That means that Gn is equal to identity for some n greater than or equal to 0. So while looking into the sender of G, we can see that G is abelian if and only if sender of G is equal to G. That means sender of G plays a similar role like G1. So the same question arises. So is there any way to iterate the formation of the sender of the group so as to create a series which begin with identity and contained in Z1, contained in Z2, and so on, where Z1 is the sender of G? And using this series, can we characterize the solvable group? That means, can you be able to show that a G is solvable if and only if this series reaches G in a finite number of steps? That means G is solvable if and only if Zn is equal to G for some n belongs to natural number or n greater than or equal to 0. So the answer is yes and no, both are there. Yes, because there is a natural way of defining such a series. It is no, because the solvable group cannot be characterized in this way. But it can be characterized as a smaller class of groups called the nilpotent groups. Now we'll see how to create such type of series. Now let G be a group and we define the subgroups inductively as follows. Z0 of G is equal to identity, Z1 of G is sender of G. Now because center of G is a normal in G, we can construct or we can define or we can form the quotient group G mod sender of G. And we can define the sender of this quotient group. That means Z of G mod center of G. And we have the projection map phi from G to G mod center of G. Then define Z2 of G as phi inverse of sender of G mod center of G. So which implies Z2 of G mod Z1 of G. That means sender of G is equal to sender of G mod center of G. So because the center of G mod, the quotient group G mod center of G is normal in G mod center of G and phi is surjective, the inverse image of the normal subgroup is a normal subgroup. That means Z2 of G is a normal subgroup in G. And Z2 of G contains center of G also. That means Z1 of G is contained in Z2 of G. So the same technique we can use to construct the remaining terms of the series. So because Z2 of G is normal subgroup of G, we can define the quotient group G mod Z2 of G. And we can define the sender also, sender of G mod Z2 of G. And consider the canonical projection map G to G mod Z2 of G and define Z3 of G is equal to phi 1 inverse of sender of G mod Z2 of G. And then we can show that similar way Z3 of G is a normal subgroup of G and contains Z2 of G. So in general, if the normal subgroup Zi of G is constructed, then we can define Zi plus 1 is equal to phi A inverse of center of G mod Zi of G, where phi A is the projection map from G to G mod Zi of G. And this means that Zi plus 1 mod Zi of G is equal to center of G mod Zi of G. So we obtain a series of normal subgroup of G, namely Z0 equal to identity, Z1 is equal to center of G, Z2 of G defined, and so on. And Z0 of G is contained in Z1 of G, contained in Z2 of G, and so on. And this series of normal subgroup of G is called the upper center series of G. Now we will see some examples of the upper center series of groups. What is the upper center series of an abelian group? Let G be an abelian group. Then what is Z1 of G is center of G. Center of G is same as G. And Z2 of G is the subgroup of G containing G. That means center Z1 of G. That means Z2 of G is a subset of G and G is a subset of Z2 of G. Therefore, Z2 of G is equal to G. Similarly, we can show that Z3 of G is equal to G and so on. Therefore, the upper center series of the abelian group G is E contained in G, contained in G, and so on. Now, what about the upper center series of S3? Suppose G is equal to S3. Then the center of S3 is same as Z1 of G is equal to trivial group. Now, we want to define what is Z2 of G. What is Z2 of G? It is the subgroup of G containing Z1 of G, such that Z2 of G mod Z1 of G is equal to center of G mod Z1 of G. Therefore, Z2 of Z2 of G is isomorphic to Z2 of G mod E. But Z1 of G is equal to E, so it is same as Z2 of G mod Z1 of G. But Z2 of G mod Z1 of G is same as center of G mod Z1 of G. So it is center of G mod Z1 of G. But Z1 of G is identity. Therefore, this is center of G mod identity, which is equal to center of G, which is equal to E. Therefore, Z2 of G is equal to identity. Similarly, we can show that Z3 of G is identity and so on. Therefore, the upper center series of G is equal to S3 is identity contained in etc. So, we are in a position to define what a nilpotent group is. A group G is said to be nilpotent if Zn of G is equal to G for some n belongs to Z. That means that G is nilpotent if the upper center series reaches G in a finite number of steps. And the smallest n is called the nilpotent class of G. And in the previous example, we have seen that the upper center series of an abelian group is E contained in G, contained in G, and so on. And therefore, Z1 of G is equal to G, and 1 is the smallest integer such that Z1 of G is equal to G. Therefore, abelian group is nilpotent class of 1. And by seeing the upper center series of S3, we have seen that it is equal to E contained in etc. So that means that series never reaches G. That means Zn of G never be equal to G for any n. Therefore, S3 is not nilpotent. Now we characterize the nilpotent group via the upper center series. So it is useful to define a related lower center series also to characterize the nilpotent group. So for defining the lower center series, we use the commutators. For any G in G, define the following subgroups inductively. That means G0 is G, G1 is commutator groups of GG, Gi plus 1 is equal to GGi, and so on. And we have seen that G1, which is same as G1, which is defined in the case of a solvable group, is a normal subgroup of G. And because G1 is contained in G, G2 is equal to commutators of G and G1, which is contained in, because G1 is contained in G, which therefore this commutator group is contained in the commutator group GG, which is equal to G1. That means G2 is contained in G1. And because G and G1 are normal subgroup of G, the commutator G1 is also a normal subgroup of G. That means G2 is a normal subgroup of G. So inductively we can define Gi plus 1, which is contained in Gi, and Gi plus 1 is the normal subgroup of G. So we have seen a series of normal subgroups of G, namely G is equal to G0, contains G1, contains G2, and so on. This series of normal subgroup, we call it as a lower center series of G. Now, what is the connection between lower center series and a nilpotent group? And in the following lemma, we will show that G is nilpotent if and only if Gn is equal to E for some n greater than or equal to 0. That means the lower center series terminate or reaches E in finite number of steps. That means the upper center series reaches G in a finite number of steps if and only if the lower center series reaches E in some finite number of steps. So let us prove this. That is, G is nilpotent if and only if Gn is equal to E. Suppose G is nilpotent. So this means what? By definition, G has an upper center series which reaches G in a finite number of steps. That means the upper center series, G has an upper center series, Z0 contained in Z1 contains in Z2 and so on, with Zn is equal to G for some n greater than or equal to 0. So here we denote Zi for Zi of G. We now show that Gi is contained in Zn minus I for all I by induction on I. So when I is equal to 0, we need to show that G0 is contained in Zn. By definition, G0 is equal to G and Zn minus 0 is equal to Zn, which is equal to G because G is nilpotent group. Because of that, Zn is equal to G. Therefore, G0 is contained in Zn minus 0. Therefore, the result is 2 for I is equal to 0. So assume the result is 2 for I. That means Gi is contained in Zn minus I. We need to show the result is 2 for I plus 1. That means we want to show that Gi plus 1 is contained in Zn minus I minus 1. But by definition, Gi plus 1 is equal to the commutator of G and Gi. But Gi is contained in Zn minus I, so this commutator group is contained in G Zn minus I. That means Gi plus 1 is contained in the commutator group of G Zn minus I. So if we can show that this G Zn minus I is contained in Zn minus I, then we are done. So we show that for showing G and I plus 1 is contained in Zn minus I minus 1, it is enough to show that the commutator group G Zn minus I is contained in Zn minus I minus 1. So let us take one element in G Zn minus I. So without loss of generality, we may assume that A is a basic generator of the commutator group G Zn minus I. So A is equal to xy x inverse y inverse for some x is in G and y is in Zn minus I. So because x is in G and G is a group, x inverse belongs to G and y belongs to Zn minus I implies y inverse also belongs to Zn minus I. Therefore the coset of x inverse, that means x inverse Zn minus I minus 1, belongs to the quotient group G mod Zn minus I minus 1. And the coset of y inverse, that is y inverse Zn minus I minus 1 belongs to the quotient group Zn minus I mod Zn minus I minus 1. But we know that by definition of the upper center series, the quotient group Zn minus I mod Zn minus I minus 1, which is same as the center of G mod Zn minus I minus 1. But the coset of y inverse belongs to this quotient group. So therefore, the coset of y inverse belongs to the center of the quotient group G mod Zn minus I minus 1. So therefore, the coset of y inverse commute with every element of the quotient group G mod Zn minus I minus 1. So in particular, it commute with the coset of X inverse. Therefore, the coset of X inverse into coset of Y inverse is same as coset of Y inverse into coset of X inverse. So by the property of the coset product, which we get X inverse Y inverse into Zn minus I minus 1 is equal to Y inverse X inverse into Zn minus I minus 1. So if you take this Y inverse X inverse to the left hand side, we get xy X inverse Y inverse is into the coset of X inverse Y inverse in the quotient group G mod is n minus I minus 1 is equal to Zn minus I minus 1. This means that xy X inverse Y inverse belongs to the group Zn minus I minus 1. That means A belongs to Zn minus I minus 1. So we have shown that if A belongs to the commutator group of G Zn minus I, then A belongs to Zn minus I minus 1. Therefore, Gi plus 1 is contained in Zn minus I minus 1. So therefore, the result is 2 for I plus 1. So by induction, Gi is contained in Zn minus I for all I greater than or equal to 0. So in particular, Gn is contained in Zn minus n, which is equal to Z0, which is equal to E. That means Z0 is a subgroup of E, therefore Gn is equal to E. That means, therefore, we have shown that if G is nilpotent, then Gn is equal to E. That means the lower center series reaches E in a finite number of steps. So we will prove the converse. Suppose Gn is equal to E. We want to show that G is nilpotent. So we first show that Gn minus I is contained in Zi for all I greater than or equal to 0. So if I is equal to 0, Gn minus 0 is equal to Gn, which is equal to identity and which is same as Z0. Therefore, Gn minus 0 is contained in Z0. Therefore, the result is 2 for I equal to 0. Assume the result is 2 for I. That means Gn minus I is contained in Zi. But by definition, Gn minus I is same as the commutator of Gn minus I minus 1. And so, the commutator of Gn minus I minus 1 is contained in, this is contained in Zi. We want to show the result is 2 for I plus 1. That means we want to show that Gn minus I minus 1 is contained in Zi plus 1. So let x belongs to Gn minus I minus 1. So let G be any arbitrary element of G. So G inverse X inverse Gx belongs to this commutator group Gn minus I minus 1 because G is in G and X is in Gn minus I minus 1. But we know that the commutator of Gn minus I minus 1 is contained in Zi of G. That means that G inverse X inverse Gx belongs to Zi of G. So therefore, G inverse X inverse Gx, the coset of G inverse X inverse Gx in is Zi plus 1, the quotient group with the coset of Zi, that means G inverse X inverse Gx Zi is equal to Zi, which means that the Gx Zi is equal to Sg Zi. That means that the coset of G into coset of X is equal to coset of X into coset of G. This is true for any coset G Zi belongs to G mod Zi. That means that G X Zi commute with every element of G mod Zi. That means that X Zi belongs to the center of G mod Zi. But we know that the center of G mod Zi is equal to Zi plus 1 mod Zi. Therefore, H Zi belongs to the quotient group Zi plus 1 mod Zi. That means that H must be belongs to Zi plus 1. So we have chosen H is in Gn minus I minus 1 and we have shown that it belongs to Zi plus 1. So Gn minus I minus 1 is contained in Gi plus 1. Therefore, the result is 2 for I plus 1. Therefore, by induction, Gn minus I is contained in Gi for all I. So in particular, for I is equal to n, we have Gn minus n, that is G0, equal to G, and which is contained in Zn. And but Zn is a subgroup of G, therefore Zn is subset of G. So Zn is equal to G. So we proved that the upper center series reaches G in finite number of steps if Gn is equal to identity. Therefore, we proved that Zn is equal to G for n greater than or equal to 0. Therefore, by definition, G is nilpotent. So in the next session, we discuss about more on nilpotent groups. We discuss some characterization and some example of nilpotent groups. Thank you.